Hi, everyone. Thanks for being here. And thanks especially to John and David for the invitation. So I'd like to describe for you some work I did recently while at the CUNY Graduate Center. This is joint work with Yannis Vlasopoulos at Tunnel in New York. And I thought I would motivate the ideas in this paper by opening with a question which I think is relevant to some of the ideas being discussed in this workshop. And that is the question of what state is being learned by a given tensor network model during training. And in particular, I'd like to think about this question in the context of the paper by Miles and David in 2016. Why this context in particular? Well, this question was asked recently by colleagues at X. Probably you all have seen this paper by John Martin, Giffrey Vidal, Chase Roberts, and Stefan Leichenauer. And they asked this very question in the case of the MNIST data set. So, what state is being learned by this MPS model in this case? Well, one plausible candidate is to consider the sum of product states associated to training images of a given label. So, product states being obtained by applying a local feature map to pixels in an image, and then taking the sum of these feature maps over all images in your training set. So, maybe this is the thing being learned during training. So the approach to sort of check this idea is to look at the amount of entanglement in this state. So on the right-hand side, here's a MPS model. You can imagine sort of partitioning images into an upper and lower half and asking for the bond dimension there. I think in the paper of Miles and David, bond dimension of size 120 gave good accuracy. And so if this superposition of product states is, plausibly the state being learned, maybe we should check its Schmidt rank and see if it's comparably low. But it turns out it's pretty high. So one thing they show in this paper is that the number of singular values of this state under this tensor decomposition down the middle, the number of singular values is essentially just the number of training images. The singular values are all roughly equal, and so there's no obvious SVD cutoff that you can do. And so this state has high entanglement, and so maybe that suggests that, all right, the state being learned during training must be something, way different than this. Or is it? So recently there was a paper a few years ago by Yi-Chen Wang in 2017 who gave a nice combinatorial argument that in fact the sum of all images of a given label is indeed a state with low rank and also can be approximated well by a matrix product state. So what's interesting about this paper is this word all images is pretty important. So you can even imagine, if I have a training set of size 1,000 or even 10,000, that's just a very small fraction of all possible ways that one can write, the number 0, for instance. And so in such a small training set, there won't be lots of overlaps between images to cause a reduction in rank. But in theory, if one had access to all possible images, all ways that one can write these digits, then Yi-Chen argues this has low entanglement in low rank. Now, I think that's an interesting paper, and so there's a pretty easy way that one can do a small experiment as a sanity check for this, just to see how this would work. So I thank Giffrey for this idea. You can imagine augmenting your training set to sort of mimic the idea of having access to all images by, for each image in your training set, you can imagine generating elastic deformations, quote unquote, of that image. You can sort of smudge it or smear it or warp it in a whole bunch of ways. Do this several times for each image in your training set. Take the superposition of all of the resulting states, and then look at the Schmidt rank or the Schmidt spectrum of that state. And so on the right-hand side, I have sort of the before and after of this. So on the top of the screen, the colors just denote the size of the training set that you start with. Before this sort of elastic deformation idea, all of the singular values are the same, and they're sort of, the spectrum is flat, right? So there's no obvious cutoff that you can do. But after you do this little sanity check and experiment and sort of generate new images by deforming them in this way, then you can see that the singular values do start to taper off. And so, you know, maybe after truncating at a certain value, then, okay, great, my state does have at least, you know, relatively low rank. So that's just a nice way to sort of see this theoretical paper, you know, plausibly, how could we see this experimentally? I don't want to dwell too much on this, though. I only mention it because I think that there are a lot of interesting questions that one could ask about this particular state, namely the sum of all of your data. I want to think about this state now in the context of language rather than images. Now, I don't know of an analogous analytical or combinatorial theorem that gives a statement about the amount of entanglement in this state in the context of language. But at least it turns out from a mathematical perspective, this state does have interesting category theoretical advantages. And that's really what my work with Giannis is about. And that's what I'd like to talk about for the rest of the talk. So I have category theoretical here in bold. And so this is sort of the main mathematical ideas in the work. So let me just say, in case not everyone is familiar, category theory is a branch of pure mathematics whose sort of trademark emphasis is on the networks of relationships that mathematical objects share. So to a category theorist, the sort of primary interest is not necessarily a fine-grained perspective into a mathematical object like a set or a group or a vector space, not sort of the internal anatomy of that object, but rather a larger bird's eye view perspective of how these objects are relating to each other. This is sort of the hallmark perspective of category theory. But what does this look like in practice? I mean, this is sort of vague. What am I talking about? Well, the idea is summed up really nicely in what is probably the most famous theorem in category theory, and that's called the Anita lemma. So the Anita lemma is a result that says any mathematical object, like a group or a topological space or a manifold, is completely determined by its network of relationships that that object has with other objects in the ambient environment. So in other words, if I want to understand something about a mathematical object like this one in the center here, then up to isomorphism, it's enough for me to know the totality of all other, all relationships that that object has with other objects in the category. So you sort of look at all morphisms out of that object, or, you know, flipping the arrows around, all morphisms in. So the Anita lemma says it's enough to study this environment, this perspective. So what we'd like to do is to adopt this categorical perspective in the context of language. So if I take this Anita lemma perspective, then, you know, if I want to understand something about a particular word or expression in language, like the word orange here, then it's enough to look at the totality of ways that word fits into other expressions in the language. So here I'm sort of, my arrows are relationships which are indicating containment, substring containment or subsequence containment. But it's sort of, you know, you can see pretty quickly that this isn't quite the whole story. It's not the full story, because there are also statistics involved with these expressions. So some of these phrases on the screen have a low probability of being spoken, you know, like orange idea, but others have a much higher probability, like orange fruit. So if I really want to understand, you know, the mathematical structure, then somehow I need to incorporate probabilities in this picture. Maybe do something like decorate these relationships with the conditional probabilities of containment attached to them. Now, it turns out this is actually, this idea can be made very precise in a formal mathematical way in the language of category theory, and that's one thing I'd like to describe for you. But another thing is, for this to be sort of useful, I'd like to make this more concrete. I'd really like to sort of pass from, classical probability theory to quantum probability theory, or from, sets to vector spaces. And that's another part of the work that we do. So there's a way to assign to every sequence or expression in language a linear operator. It'll turn out to be a reduced density operator, and that passage will be provided to us precisely by this sort of sum of all expressions in language state, sort of analogous to the one in the context of images. Even better, this passage from left to right preserves the mathematical structure. So it preserves the categorical structure, and it's compatible with probabilities in a really nice way. So that's what I'd like to describe for you, sort of the three things on the screen here. What does it mean to have a category of sequences, a category of reduced density operators, and what exactly is the passage from left to right? Now, I've used the word category a few times already, so let me just say, in mathematics, the word category has a precise formal definition behind it. So I think that will be helpful for me to say, just to make sure that everyone's on the same page. So a category consists of objects together with morphisms or arrows between them. And we ask that these arrows compose. So, going from X to Y and Y to Z, I can sort of travel along both paths to get from X to Z. And then we also ask that these data satisfy sensible conditions like, composition is associative, and every object has an identity arrow attached to it, which I've not drawn on the screen. But the point is that this very abstract definition is a nice template into which a lot of mathematics fits very neatly. So some famous examples of categories include sets and functions. So my nodes on the screen could be sets, and the arrows could be functions between them, or the nodes could represent groups. Arrows could be group homomorphisms, vector spaces and linear maps, the list goes on. So these are some famous categories. There's another category that I'd like to give as an example, which will be maybe easier or simpler to think about. And that is the unit interval. So the set of all numbers between 0 and 1 is a perfectly good example of a category. The numbers in this set are going to be the objects in my category. And if I just think of the usual ordering, when one number is less than or equal to the other, this turns out to be a good notion of morphism or arrow. So I'm drawing less than or equal to rather than an arrow, but it fits the axioms quite nicely. But here, there's nothing really special about numbers. More generally, any set together with what's called a preorder. So a preorder is just, you can think of it as a notion of saying when one thing is bigger than another. Technically speaking, a preorder is a binary relation that's transitive. So transitivity is really my composition in a category, and also reflexive. So every element is, comparable to itself. So not just the unit interval then, but you can think of the entire real number line. That's also a category with the usual notion of ordering. These are examples of preordered sets. Now, for the purposes of this talk, there's a very specific preordered set, or a very specific category, and that is one comprised of sequences. So here's the main example that we really want to focus on. Let's suppose we start with a finite set X. Think of X as the set of atomic symbols in your language. For us, we can just think of X as the set of all English words, for example. And what I'd like to do is to consider the subset of all valid sequences of length at most some fixed length n, capital N. So I have these sequences, and I can just compare them by sort of subsequence containment, so subsequence of consecutive words, and then look at containment of that. So, I climbed is a sequence of length 2, and it sits inside I climbed the tall mountain, a sequence of length 5. Or, if I think back to that colorful network involving the word orange, I can have something like orange sits inside ripe orange, which sits inside small ripe orange. Now, it's easy to check then that this defines a pre-order on this set of sequences. So this is a perfectly good example of a category. And in fact, it is the category that I had in that colorful picture a few slides ago. But as we mentioned then, that's not quite all that we want. There's more, namely probabilities attached to these containments. So how do we incorporate probabilities into this picture? Well, just suppose we start with a probability distribution on our set of sequences of length n. So I have this joint distribution, therefore I have marginals and I have conditionals. I have everything. So the intuition then, what we'd really like to do, as we mentioned earlier, is to simply decorate these containments with the corresponding conditional probability. So, all right, orange sits inside of ripe orange. So what's the probability of seeing the phrase ripe orange given that orange is there? Whatever that number is, I have access to it, so I'm going to decorate this containment with that number. Similarly, ripe orange could sit inside some larger expression, and I want to decorate that containment with that conditional probability. And then the nice thing to observe here is that, again, I have this sort of transitivity going on, or compositionality. And so anytime you have compositionality, this is exactly what it means really to have a category theoretical structure. So in this case, it turns out that because I have a joint probability distribution on a set of sequences, the conditional probability for small ripe orange given orange, for example, is precisely the product of these two intermediate probabilities. And when you sort of write all of this out and see what it means, there's a formal phrase attached to this. So this structure, this category theoretical structure, together with these decorated probabilities, means we have what's called a category that is enriched over the unit interval, or over probabilities. Now, the intuition is all on this slide. It's pretty simple, but this idea of enriched category theory is sort of a key idea, and so I think it would be helpful to just say a little bit about this word enrichment. So let me just take a brief detour and say, in ordinary category theory, we ask that the collection of arrows between objects form a set. But in enriched category theory, the collection of arrows may not be a set. So what does it mean to not be a set? Well, you can imagine that X and Y here are my objects. Maybe these are vector spaces. And so the arrows between them here are linear maps. Now, the set of linear maps between two vector spaces is more than a set. It's a set with extra structure, namely it's a vector space. So that's an example of this enrichment. So in this case, we say that the category of vector spaces is enriched over vector spaces because this set is itself a vector space. So you can imagine other scenarios where maybe my set is enriched over another category, not vector spaces, but we talked about a category already, namely the unit interval. So we're in a situation where our objects are sequences. There's at most one arrow between any two sequences. That one arrow corresponds precisely to a number, namely the conditional probability of containment. And so if I just sort of replace that arrow with that number, I'm enriching my category of sequences over probabilities, or over the unit interval, sort of analogous to the vector space scenario. But then, one checks the axioms. You have to make sure that compositionality works and so forth. And indeed, this does work. So this is the structure that we're interested in. Language, I can view them as sequences. I can incorporate probabilities in this nice category theoretical way. So that's what's going on the left-hand side here. But again, we would like to make this a little bit more concrete and really map over into the world of linear algebra. So now let me describe for you a way to associate to each sequence in my language a linear operator, and see how this sum state is involved. So here's the main idea. I'm in particular going to consider positive semi-definite operators, or unnormalized reduced densities on my free vector space generated by my finite alphabet X, operators associated to sequences. Now, just like we can compare sequences and obtain a pre-order on a set, there is also a way to compare positive semi-definite operators on a given Hilbert space, and it's called the loner order. So one says that a positive semi-definite operator rho is less than or equal to rho prime, if and only if their difference is again a positive semi-definite operator. And the nice thing is that the assignment that I'll describe for you that takes a sequence and produces a positive semi-definite operator is actually compatible with the orderings on sequences and on operators. And it's actually compatible in this order reversing way. So in the language of category theory, we call this assignment a functor between categories, or the fact that it reverses the order means that it's a contravariant functor. But let me describe for you, given a sequence S, what exactly is this operator rho sub S? So it's pretty simple. We started with a probability distribution on our set of sequences, and that probability distribution can represent it as a unit vector in the free Hilbert space generated by the set of sequences, which is isomorphic to the n-fold tensor product. So quite simple. Just take the weighted sum of all sequences of length n and weight them by the square root of their probabilities. So because I'm working in a free vector space, the vector representation for a sequence of length n, which I'm calling S, is just a product of one-hot encodings, if you like, or a product of standard basis vectors for the individual words that comprise that sequence. So this is really my superposition of product states, and now I'm just weighting them by the square root of their probabilities to ensure that it has length 1. So given our probability distribution, I get a unit vector in this way. And given this unit vector, I can now define operators associated to sequences of length at most n. So given a subsequence, say of length 3 in this picture, I take the product state associated to that subsequence, compose it with my vector psi on the previous slide, form projection onto that vector, and just trace out the remaining sites. Of course, I want to leave, let's say, the rightmost site open so I do get an operator in the end. Now, in this picture, I plugged in my sequence of length 3 onto the right, but you can imagine plugging it in anywhere and tracing out the remaining sites. But the thing to notice here is that the operator that I get, I'll call it rho sub S. This is a reduced density in quotation marks because it's positive semi-definite, but may not have trace 1. So here's my assignment to operators, and now there are a few observations that I can make, so we can just go through these quickly. The first observation sort of takes us back to our original idea of the sort of Anita perspective. So because the partial trace, let's say this, on the previous slide, I was looking at a phrase of length 3, but imagine I just have a word of length 1 now. The partial trace really involves a sum of all words that precede this sequence or word that I'm focusing on. So, my diagrammatic picture in the middle here really means that the density for a given sequence or word that I'm interested in, like orange, decomposes as a sum of densities or operators associated to each phrase that ends in that word, that ends in orange. So, the density for orange is the density for ripe orange plus small orange plus, like orange and so forth. So I like this decomposition result. It's simple, but it goes back to this Anita perspective that we mentioned earlier. And it suggests that as far as the linear algebra is concerned, a word like orange is the totality of all expressions that end in that word. So I think it really captures the Anita lemma in a nice way. That's one observation that we can make. Another observation goes back to this order reversing idea that I mentioned earlier. So you can imagine taking one of the terms on the right-hand side, like the density for ripe orange, and sort of moving it over to the left. And what you get is a sum of positive semi-definite operators, which is precisely what it means to say that the density for orange is greater than or equal to the density for ripe orange under the loner order. And so just taking a step back, I have, you know, words or sequences, I map them to operators in this way, and this assignment reverses order the orderings, and that's precisely because of this decomposition that I get from the partial trace on the previous slide. So the simple way to say this is that, okay, I have a functor now, and it's contravariant because it sort of flips the arrows. But you know, we've mentioned a few times that what's really interesting to get kind of the complete picture is to incorporate probabilities. We know how to do that on the top half of the slide. We know how to decorate conditional probabilities here using ideas of enriched category theory. So I'd also like to see that appear naturally on the bottom half. And it turns out that that does indeed happen. So the first thing to notice in this direction is that the trace of an operator associated to a sequence is precisely the marginal probability of that sequence. And that's not, you know, not too hard to see. My vector psi was essentially a sum of joint probabilities. So the partial trace is just, you know, summing over all variables except for the one that I'm focusing on, and that's just precisely marginalization. So what I can do is divide or normalize my reduced densities by their trace, or by the marginal probability. This gives me a true density operator with trace 1. And it turns out that the density for a word or an expression has an analogous decomposition, but this one now is weighted. So I have that the true density for orange is, you know, ripe orange plus small orange plus and so on. But now there's coefficients weighting each of these operators. And these coefficients are precisely the conditional probabilities that we had discussed earlier. So it's nice to see that they sort of arise in this natural way. But at this point, I'd like to make the mathematics a little tighter. So it turns out that density operators or operators with trace 1 are not comparable under the loner order. So I don't really want to normalize here. What I'd really like to do is to look at my unnormalized reduced densities, but just extract those coefficients or those conditional probabilities and sort of decorate, quote unquote, the ordering just like we did in the case of sequences. And so that's the intuition, but it turns out the mathematics works very nicely in this way too. So we simply define the set of all linear operators or all reduced densities associated to sequences in this way. These form the objects of a category, and this category again is enriched over the unit interval in the same way. You can, in fact, make this even nicer by involving the traces of these operators, which their quotient turns out to correspond exactly to conditional probability. So in this case, the ideas are sort of the same as in the sequence case, which is nice. And the punchline for all of this is that the mapping from sequences into linear algebra in the way described using this vector psi, it's compatible with both the orderings as we noticed, but also compatible with the probabilities. And this is precisely what it means to have an enriched functor between categories that are enriched over probabilities. So it's nice to see that the mathematics works out quite nicely in this scenario. And that's sort of the main result of the paper is that the category theory works really nicely, and it all sort of rests on this one vector psi, which is sort of the sum of all expressions in your language, weighted by the square roots of their probabilities. So of course, all of these statements that I'm making are sort of model independent statements. So I'm not assuming any tensor network factorization on psi, but it could be really interesting to explore the mathematical structure further, once I've chosen a specific tensor network model to work with. And so that'll be interesting for future work. And I think I'll leave it off here and happy to take any questions.